All right, so in this video, we're going to be looking at Markov chains. Markov chains are a type of discrete dynamical system with special properties because the change of state matrix is representing probabilities. And so it has special properties, particularly in terms of stable solutions and things like that. So let's consider a graph of a three-state system below. So we have three possible states that we could be in. One of them is state A, one of them is state B, and one of them is state C. As we change from discrete moment in time to discrete moment in time, say, again, a month, a day, a year, depending on how often we measure it, we could, if we're in state A, stay in state A. So that's this arrow that points back at A. We could go to state B, or we could go to state C. If you are starting out in state B, you could stay in state B. You could go to state A, or you could go to state C. And if you are in state C, you could return to state C, go to state A, or go to state B. And again, each of these is associated with a probability relationship. And so the probabilities from any one state all have to add up to 1. Now, in each of these circumstances, there is certainly a possibility of remaining in the same state. And we're going to see some circumstances where we have special cases where maybe you end up in a particular state and then you can't leave. But in most cases, when we're dealing with Markov chains, we're dealing with circumstances where all of the possibilities are available. You can move from any state to any other state. Now, in linear algebra, we can deal with discrete time Markov chains where the probabilities are associated with a jump in each time step. So for example, the probability of moving from, say, one party to another, political affiliation, Democrat, Republican, Independent, might change for some voters from election to election. There's a certain probability of staying within one party, but you could vote for the same party again in the following year. So you might change or you might not. Now, the chain idea comes from the list of states that a particular element of interest might transition through. So similar to the discrete dynamical systems in general, there's essentially a trajectory of how the process is moving through time. Now, let's consider, again, another three-state system. In this case, we're representing the probability of moving from the state A to the state B, and we're going to designate that to be 25%. The probability of moving from state A to state C is 15%. That means there's 60% chance of remaining in the A state. If we have a probability of moving from the B state to the A state is 20%. The probability of moving from the B state to the C state is 5%. That leaves 75% chance of remaining in the B state. And lastly, if there is a 10% chance of moving from the C state to the A state, that would give me here. And a 15% chance of moving from the C state to the B state, that would be here. That would leave behind 75% chance of remaining in that third state. And then this is our representation. This is our change of state matrix. So here I've plotted these probabilities on the graph. 60% to stay in A, 25% to go to B, 15% to go to C, and so forth. Now, because the columns of the matrix P represent the state the object starts in, and the rows are the states the object ends up in, because these are probabilities, the entry in each column must add up to 1. That is a requirement for Markov chains because they are representing the probability of a transition. Now, the Markov chain terminology comes from the behavior of a specific object run through such a system. What we are interested here is in studying the behavior of the system itself. So if we run hundreds of objects through the system and look at what happens to them in the long run, what kind of behavior can we expect? If the three states are three types of, let's say, food eaten by caged rats at each feeding, we aren't so much interested in what one individual rat is doing, but in the long-term behavior of the population. For instance, maybe you're trying to plan about how much each type of food is required to be purchased at regular intervals, given previous feeding cycles. So consider our P matrix from before. Suppose that at a certain feeding time, we call the situation the state vector x of k. There are 50% of the rats in the population eating from feed C. That's this guy down here, 20% from feed B, and 30% from feed A. We can organize these in a vector with the same order in the matrix, so A, B, C. And these represent all the possible states. And again, the entries, because these are representing proportions, they have to add to 1. We can also do this with counts, although proportions is easier to work with in terms of interpreting the context in any type of situation. So our examples are going to stick with these proportions. Now, accounting for the entire population, we can multiply this vector by the change of state vector in order to get how much of the population will be eating at the feeding station in the next cycle. So I multiply my 0.3, 0.2, 0.5 by this matrix, and I get 0.27, 0.3, and 0.43. And if we continue this procedure, we can find the sequence of states that the system will pass through over time. So if I multiply my initial state by the matrix, I get the next state in the chain. And if I multiply that matrix by the transition matrix, I get the next one, and so on and so forth. And what I can actually do is I can jump to any point in the sequence because I'm just continually multiplying that initial state vector by the Markov chain matrix over and over and over again. If I want to jump ahead n steps, I can simply multiply by p to the n power because I'm multiplying that initial state matrix by the same matrix over and over and over again. So if I plot out, I do the calculation for the sequence of values for how much each of my how many of my rats are eating at any particular feeding station over time, I end up with, or food type over time, I end up with this trajectory. And if I keep calculating it, I find that the entries start to look kind of the same over time. So they stop changing dramatically. And what it appears to be happening is that they are approaching a steady state. Now, with each step, the changes in probabilities for objects get smaller until all the vectors in the sequence start to look alike. So up to a certain tolerance for the calculation of the system, the limit will converge to what is called the equilibrium vector. And this is a vector Q such that when you multiply the Markov chain matrix by that equilibrium vector, the result is the equilibrium vector. So in other words, the equilibrium vector Q multiplied by the Markov chain, nothing happens. Now, what this suggests actually is if we think about this in terms of eigenvalues and eigenvectors, is that the eigenvalue for Q is 1, and it is an eigenvector of the matrix P. Now, there are two methods that we can use for calculating the equilibrium vectors for a Markov chain. One is technology intensive, and the other we can do algebraically. So the first is that we can raise the matrix P to some very, very large power. Again, we can do this with a calculator quite straightforwardly. The initial condition doesn't matter in the long run. So the long run behavior is actually contained in the matrix itself. And then the second can be more easily done on paper, and that is to solve this equation as basically as if it was an eigenvector problem. So let's first start by raising the matrix P to a very large power. So enter this into your calculator, for instance, and then I usually start in my calculator by raising the matrix to about P60. So P to the power of 60, and then I square it a couple of times until the numbers in the matrix all look the same. Every column is identical. Now, exactly how big a power you will have to use in your calculator is going to depend a little bit on the entries of the matrix. Sometimes the equilibrium vector will take a little bit while to find. Technically, we're looking for the limit as k goes to infinity, and this isn't quite p infinity, but within the tolerance of our calculator's rounding errors, this is fine. Now, when you've gotten to that state where you're actually at the equilibrium position, you can often hit convert to fraction, and it will convert to actual fractional values rather than random decimals. And when I actually squared this one more time, my P60 matrix, to get P120, I was able to convert all of my fractions, all of my matrix entries to fractions. And again, you know you've gotten to your equilibrium position when all of the columns are identical, and then any one of these columns is equivalent to your equilibrium vector. Now, in this case, you can double check this. If you multiply the original matrix by this vector, and we can do it by hand, or we can put it in the calculator to do this math, you'll actually find that the arithmetic does lead you to exactly the same vector. So that is proof that this is, in fact, the equilibrium vector because it satisfies the definition. Now, for the second strategy, if we want to do this algebraically, we're going to move Q over to the other side of our equation. And just like we would with eigenvalues, we're going to factor the Q out. In order to do that, we multiply Q by an identity matrix so that in our parentheses here, we are actually subtracting like from like, a matrix minus a matrix, and not a matrix minus the number 1, because you can't subtract 1 from a matrix. They don't have the same dimension. So the identity matrix ensures that it does, in fact, work mathematically speaking. Now, to find Q, we need to find the null space of this P minus I matrix. So again, this is just like doing eigenvalues and eigenvectors. Here, since there's no lambda here, we're treating lambda as if it's 1. And when you do this subtraction, you get this matrix. Now, it's not, because it's a 3 by 3 matrix, it's not immediately obvious that this is, in fact, dependent. These are not like decimals involving square roots or anything. So you can put this in your calculator and row reduce it a little bit in order to get to a state where we can actually see that it's dependent. And if you put this into your matrix, into your calculator and row reduce it, you do end up with this matrix as the reduced form. And you can see you have a row of zeros and you have a free variable. So that is a sign that the matrix is in fact dependent. Our top equation is x1 minus 1.1 x3. And our second equation is x2 minus 1.7 x3. Both of them are equal to 0. That means x3 is equal to itself. That is a free variable. And so if we move the x1 and the 1.1 x3 and 1.7 x3 to the other side of our equation, and then we set x3 equal to 1, we get this vector. Now, the downside of this is that, in fact, these don't obviously add up to 1, and we started out with state vectors that were probabilities, not counts of things. So we need to convert these to probabilities. And so what we're going to do is we're going to have to rescale this so that the sum is 1. So we're going to first find out what the sum actually is. So 1.1 plus 1.7 plus 1 is 3.8. And then we're going to divide our vector here to get our equilibrium vector by the sum of all of the entries. So we're going to divide these all by 3.8. And if you divide all of these by 3.8, you get 11 over 38, 17 over 38, and 10 over 38. And 10 over 38 reduces to 5 over 19, which is the same equilibrium vector we found by our technology process. Now, how do we know for sure that in a Markov chain, there is an equilibrium vector at all? Couldn't the system just keep changing forever? We have theory actually to show that under certain conditions, one and only one equilibrium vector has to exist. And one requirement is that all of the states must be accessible from all the other states. If some states are isolated, then there will be more than one equilibrium vector. So when we did that row reducing above, we would get more than one free variable. And which one you end up in will depend on where you start. So if I consider this system with 4 states, state A and B are communicating with each other, and state C and D are communicating with each other. But there is no way to get from, if you're in state C, to get to state B, or vice versa, for example. So again, we would say that this matrix lacks the proper communication, and therefore there will be 2 equilibrium vectors since there are 2 separate pieces to the system. And so whatever equilibrium vector you end up with will be a linear combination of those 2 equilibrium states, depending on the proportion of people or objects that started out in this AB context and the proportion that started out in the BC context. Now, in a matrix like this one, then you'll be able to get only one equilibrium state. So even though A and B, A only goes to B, B goes both to A and C, C also communicates with B, and D communicates with A. So regardless, there is a chance that if you start with A, you might go to B, and if you're in B, you might go to C, and if you're in C, you could go to D, and if you're in D, you could go back to A, and that means there is a way to get from any state to any other state in the matrix, and therefore there is sufficient communication in this matrix that you could end up anywhere in any state from whatever state you start in. And in that kind of a situation, there is only one equilibrium vector. Now, one type of Markov chain that you could encounter is one that has an absorbing state. So for instance, a state where once you get into that state, you're stuck there. So an example might be, for example, being healthy, being sick, and being dead. Once you are dead, and you do not come back alive. So, for instance, you could have a situation like this where healthy stays mostly healthy. You might get sick, and there's a small possibility that you could die. If you're not well, you may stay unwell, but you could get better, or you could die slightly more frequently. But once you're dead, you're dead. For problems like these, it may take a very long time for the matrix to settle down if you're trying to do the computational approach. But it should be very easy to establish that, in fact, the equilibrium vector must be 0, 0, 1. It took me about squaring the matrix about 13 times, or about p to the 8,000 or so, in order for my TA84 to get the decimal places to stop popping up again. So you have to get like, you have to get past the rounding errors in the calculator. So like 13 or 14 decimal places. as they approach zero. And so that took quite a long time, but it did eventually get me there. Algebraically, you could also easily show this, that x3 would have to be 1 and x2 and x1 would have to be 0 in the long run. Now, in this case, suppose that we have a two-state system. In one state, people are living in the city, and the second state is people living in the suburbs. Suppose the probability that at any given year someone is living in the city that they move to a suburb is 20%, and someone living in a suburb moves to the city is 8%. So given Markov chain matrix that models the system, and suppose that in 2013, the percent of residents living in the city is 64%, and the percent of residents living in the suburbs is 36%, what percentage of all people will be living in the city in 2015? And in the long term, what is the percentage of people who will be living in the city versus the suburbs? Now, very typical for problems like this to leave out one of the probabilities, because once you have all but one, you can use the complement property to find one that's missing. So here, if moving from the city to a suburb is 20%, that means 80% of the people stay in the city. Here, if 8% move from the suburbs to the city, then 92% remain in the suburbs. And again, we confirm that each of the columns adds to 1. Now, I will also just caution people here that if you're using Wikipedia to do some of these matrix operations, they often will multiply on in their write-ups, they will multiply on the left side of the matrix and not on the right side of the matrix. And so they will treat their rows as adding up to 1 and not their columns adding up to 1. This completely changes the behavior of the system. If you set up the rows to be equal to 1 and then you multiply on the right side of the matrix as we're doing, that will not work, and you'll get the wrong answers every single time. So just be careful about the notation and the operations that the sources that you're using are doing, because they will be different depending on the default assumptions that they're making about what side you're multiplying your matrix on. All right, so they also have to match the order. So city, suburb have to go left to right, top to bottom in the same order. Now, our current vector state was given as 64% in the city and 36% in the suburbs. If this represents 2013, so 2015 is 2 states away. So we can get there by taking our P matrix, squaring it, and then multiplying it by initial state vector, and we get this. So according to this, after 2 years, about 53% of the population will be in the suburbs and 47% will be living in the city, roughly. And then if we want the equilibrium vector, again, we can do this computationally, or we can do this mathematically. Here I find I did this algebraically. P minus I gives me this matrix. This is clearly dependent. And so if I solve for one of my equations, x1, 0.2 x1 minus 0.08 x2 is equal to 0. That gives me x1 is equal to 0.4 x2. Again, that gives me this vector, but this is not properly scaled. So I divide by the sum of these entries, which is 1.4, and that gives me 2/7 and 5/7 when I simplify. So that means that in the long run, approximately 29% will be living in the city and 71% will live in the suburbs.